All right, we're back. We'll work through a few more examples. We're going to do some more of these transitions between two different energy levels for either hydrogen or mercury. And just as a reminder, the general procedure is to do so you'll be told the two energy levels that the electron is transitioning between. Your job is to find the difference between those energy levels using the reference table, convert that answer, that is in electron volts, into joules, and then use this equation, the energy of the photon is equal to h times f, where h is Planck's constant, to find the frequency, and then to use the frequency table or chart in your reference tables to look up what type of radiation that is, what type of light that is. So again, I'll narrate the first one, then for mercury, I'll write them down. You can check your work with mine, and then we'll move on to some other examples, because you're never just going to be given something like this. This is just to get you used to the process. Usually you'll have some other sort of description going along with it. Okay, so hydrogen from n equals 6 to n equals 1. The n equals 6 energy level, as you can see, is negative 0.38 electron volts. N equals 1 is negative 13.6 electron volts. So we use this equation found in the reference tables. The energy of that photon is equal to the difference in energy levels, and do the initial minus the final, which is different from usual, in this case in order to get a positive answer for the energy of that photon. So what I say, that was, okay, negative 0.38 eV minus a negative 13.6 eV. 13.22 eV. We have to convert that into joules. And we have to find the frequency. We find that the frequency is 3.19 times 10 to the 15th hertz. We look at the electromagnetic spectrum diagram. That's very clearly greater than the upper bound for violet. 10 to the 15th is here. That's to the left of that. So we're somewhere in this range. That must be ultraviolet light. Okay, I'm going to do the next three. You can check along with me, but I'm going to stay mostly silent before I get to the other questions. Okay, mercury. So that one is also UV light. Oh, I completely did that one wrong. Oh. I'm just going to cheat and do that. No, I won't. I'll redo it. B. Let's see. B is 574. This should be 3.26. The energy in joules is 5.216 times 10 to the negative 19th joules. Okay, so we end up with a frequency of 7.87 times 10 to the 14th hertz. And actually, that still is just barely outside the violet, the upper range for violet, so it is still UV light. But okay, so I apologize for screwing that one up immensely. All right, so let's do mercury, B to A. It's also got to be UV. Last one. Okay, I... Okay, and this one we'll actually have to read carefully. 5.19 times 10 to the 14th hertz. Now, let's see here. You can't tell exactly whether that's going to be infrared or ultraviolet or visible light just by looking here. You have to look to the little expansion here. 5.19, that looks like it falls right between the markers for yellow. Here's the lower bound for yellow, here's the upper bound, just below the upper bound. So, this is going to turn out to be yellow light. That's very close to green light, but we're still going to call it yellow. Okay? So again, that's the basic process for figuring out what the color of the emitted light is. We're going to go to some examples now. Okay, there we go. All right, so number 2. In a hydrogen atom, an electron absorbs a photon and jumps from the n equals 1 state to the n equals 4 state. What was the energy of the photon? So in this case, we have something being absorbed. Remember, I told you for absorbed, what you really want to do is this equation, so you don't have like weird negatives to deal with. E photon equals EF minus EI. We just need to know, because the photon jumped up in energy, up a few energy levels, we need to know the difference between those energy levels. That should be equal to the energy of the photon. For hydrogen, n equals 1 is negative 13.6. That's the initial EV. And n equals 4 is negative 0.85. So we're going to write negative 0.85 EV for final minus an initial negative 13.6 EV for where it started. And if we do that math, we'll see that the energy of this particular photon must have been 12.75 EV. Okay. Now, if the electron then falls to the n equals 2 state, it doesn't have to fall all the way back down. It can fall to an intermediate state. What is the frequency of light that will be emitted? So now we have to go and find the frequency. This is pretty much what we just did if we're doing a few minutes ago. So this is E photon. Now it's being emitted, so we do EI minus EF. E photon, the initial state, this time it starts off at n equals 4, so that's this, negative 0.85 EV minus a negative, and n equals 2 is negative 3.4 EV. So the energy of this photon that gets released is 2.55 EV. We have to convert that to joules. That's from the front of the reference tables. And we see that this is 4.08 times 10 to the negative 19th joules. Now we need to find the frequency. We use this equation, E equals HF. Oh, I'm going to run out of room, aren't I? We find that the frequency is 6.15 times 10 to the 14th hertz. And just for good measure, we'll figure out what type of radiation that is. It's times 10 to the 14th, so we got to be a little careful. But if we go to the spectrum, we see that 6.15 times 10 to the 14th is right between the markers for blue. So this must be blue light. Okay. Next, a 6 electron volt photon approaches an electron in the ground state of a mercury atom. To which energy level will the electron transition? So if it's in the ground state of mercury, that means that an energy level corresponding to negative 10.38. If it absorbs a 6 electron volt photon, it should go up to negative 4.38. But if you look, there isn't an energy level there. It's somewhere between D and E. Does that mean it goes up to D and then just kind of stops there and the other energy gets dissipated? Does that mean it just kind of goes halfway between them and we'd say it just reaches halfway between D and E? No, neither of those are true. The electron's not going to transition to another energy level. So this answer is none. It won't even move. It won't even absorb that photon because no energy level is exactly EV higher. Nothing will happen. In order to be absorbed, a photon has to be exactly the difference between the current energy level and another energy level, another higher one. Okay, a second photon comes along and causes the electron to transition to the I energy level. How much energy did this photon have? So if it's in the ground state, or A state, and it has this much energy, and it goes up to I, where the energy level is negative 1.56, the photon must have had exactly the difference between those energies. So, since this is an emitted photon, or an absorbed photon, we're going to use E photon equals EF minus EI. The final energy level, as I just showed you, is negative 1.56 eV minus a negative for the initial state, 10.38 eV. That photon must have had an energy of 8.82 eV. Now, C says, what was the wavelength of this photon and what type of electromagnetic radiation was it? Well, remember, in order to get the wavelength, we could find the frequency, but we could just as easily find the wavelength by this equation, where frequency is equal to C over lambda, so that's why I'm using that as a replacement. But we can't just plug this in, we have to convert this to joules first. .4112 times 10 to the negative 18th joules. Remember that C stands for the speed of light, which for our purposes is found on the reference tables right here. 3 times 10 to the 8th meters per second. All over lambda. So essentially, if we take that number, 1.4112, and that's what we're dividing these two numbers by, we should find out what lambda is. I get that lambda is equal to, let's see, 3, 6, 7, 1.41 times 10 to the negative 7th meters. Now, I'm going to do something bad. Usually, let's see here. I really shouldn't do that. Let's find the frequency, okay? Whenever you go to use this table, you really want to use the frequency, because if you're 1 or something times 10 to the 7th, if you're in this range right here, it's really hard to tell whether you're talking about ultraviolet or infrared or visible light. However, it's very easy if you know the frequency because you can just match it up with this table. So let's find the frequency. So that's part of it. V equals F lambda. We know the speed of this wave is 3 times 10 to the 8th meters per second. We're looking for the frequency. We know that the wavelength is 1.41 times 10 to the negative 7th meters. The frequency is, okay, so it's what I thought, 2.13 times 10 to the 15th hertz. And if we look, that must be, since it's higher than this and it's 10 to the 15th, that must be in the ultraviolet range. So that's just a good guide of thumb. Whenever you're asked what type of radiation something is, you got to know the frequency. Okay, that's where I would draw the line. Don't try and tell just from the wavelength. We'll do the last 3 examples and a little demonstration when we come back.